Hi, and welcome to the Foundations course Lesson 7, Modeling Basics, Part D on Poisson Regression. So, last lesson we looked at modeling binary outcomes with a logistic regression model, and now we are going to look at modeling rate outcomes using Poisson regression models. This will be a very short lesson since there are many similarities between logistic regression models and Poisson regression models. The summary table that we're all familiar with tells us that in Poisson regression models, we are actually modeling a time-to-binary event outcome in the form of aggregated event rates using a log link function and the rate ratio as the measure of effect from exposures, and the variables have a multiplicative effect. Let's posit what rates actually are. A rate is defined as the count of new events per person per unit time. So that means that we don't only look at a number of events occurring. So that means that we're not only looking at the number of events occurring as a proportion of the total number of patients in a cohort, but we're adjusting our outcome measure for the time that an individual is exposed to the risk of developing an event. And this type of outcome is typically used in larger studies, such as in the field of public health. An example of a typical event rate outcome is the incidence of global cancer mortality, which can be expressed by a number such as 120 per 100,000 per year. Rate is denoted as a Greek letter lambda, and it is calculated by taking the number of events, which we can symbolize with the small letter d for diseased, and then divided by the total person years of observations, which we can denote as the capital letter T for time. And rates have the characteristic that when they are small, that we can calculate risk up to time point t as the product of lambda times t. Furthermore, when the time interval t is small, we can calculate lambda by dividing risk with small letter t, the time interval. We already know that we can describe the sampling distribution of rates by the Poisson distribution, but there's also an assumption that the events occur at random and are independent. Does this all sound familiar to you? We already discussed event rates, lambda, and the Poisson distribution in lesson 2, where we talked about the probability distribution of near simultaneous events. In Poisson regression models, we want to compare rates between two groups, and for this purpose we use the rate ratio, which can be calculated as the rate in the exposed group divided by the rate in the unexposed group. And this formula is pretty similar to that of the odds ratio, so that when the event rate is rare, the risk ratio, rate ratio, and odds ratio are near equivalent. Alright, let's move on to the Poisson regression model. So we are modeling event rates, and we use the log function so that we get the equation log disease rate is beta 0 plus beta 1 times x1 and so on, plus the residual factor e. And as the measure of the effect of exposures or variables, we use the rate ratio, which has a multiplicative effect. And as a test for significance of single parameters, we can use either the wall test based on a z or chi-square statistic, and the score test based on a chi-square statistic. If we want to test the entire model, we can either use the likelihood ratio test or the Akaikis information criterion, and the model fit is usually expressed as the area under the curve value. This approach is identical to the one used in logistic regression, so we are actually modeling the log rate but use the log as a link function to the equation beta 0 plus beta 1 times x1. And what those regression coefficients mean is the log baseline rate plus the log rate ratio. And if we take the anti-log of this, we can determine the rate in the unexposed group as the exponent of beta 0, which is equivalent to the baseline rate. And in the exposed group, we have to take the product of the exponent of beta 0 and the exponent of beta 1, which is equivalent to the baseline rate times the rate ratio. And the output by most statistical software packages looks equivalent to that of a logistic regression model. Here, an example for a simple model with just one categorical variable, and an example with two categorical variables and a continuous variable. Just remember that in Poisson regression model, we're not modeling the log odds of the disease, but we're modeling the log rate, and we are using rate ratios instead of odds ratios. So that's it for Poisson regression modeling. Easy, right? Get ready for the last part of modeling basics on Cox proportional hazards regression.